All right, guys, how you doing? This is last section of chapter 5. It's on the solid states. Like I said, it's all about gases, liquids, and solids. Mostly gases and solids are the main focus. So we have this chart before. You have your structure, either ionic, covalent, metallic. So ionic bonds obviously going to be giant ionic. Metallic is going to be giant metallic. Covalent, you have your covalent network solids. So those are your giant molecular structures, diamonds, quartz, graphite. And then you have your smaller ones. You have simple molecules. Those are your gases, water, diatomic elements. And then you have the big molecules called your macromolecules, like proteins and stuff like that. All right, this chart is important. All right, it's called. You need to know like examples and their characteristics for these different groups. For giant ionic, basically it's a crystal structure lattice. They have repeating arrangement of the particles like salt, sodium chloride. These are very similar in metallic compounds as well, and some covalent compounds that form crystals. But it's called a lattice structure, and basically it's a repeating arrangement of ions and atoms and molecules. You have different type of lattice structures. You have like cubic centered, face centered, and hexagon. So examples: sodium chloride, magnesium oxide, obviously ionic compounds. Particles inside are ions, positive and negative ions. What's forcing them together is the electrostatic forces, so we know that. They're solids at room temperature. They have a high melting and boiling point. They're very hard, but they also break, so like you can shatter it with a hammer. They do conduct electricity, but only in liquid state, so molten state, very high temperatures, and they are mostly soluble in water. Not sure why that's not showing up. Okay, so you can make solutions out of them. Giant ionic. Here's two structures. You have sodium chloride and magnesium oxide. It takes a high force to cause them to break. Which ionic compound has the higher melting point and boiling point? So in this case, you're looking at their what's holding them together. So their electrostatic force. Which one has a higher electrostatic force? So sodium and chlorine are both +1, -1, where magnesium is +2, -2 for oxygen. So the +2, -2 has a stronger hold because of a stronger. There's a +2 and a -2 will have a stronger electrostatic force. That means it should have a higher melting point and boiling point. All right. Basically, all you need to know is giant ionics have very hard, and they will split, meaning they're brittle. So you do need a strong force to it to split them. Okay, so in metals, they're more ductile, meaning they are going to shape, where in ionic crystals they'll completely break. So there's a difference between metals and ionic structures, that metals are going to bend and malleable, so they're going to just slide, where ionic crystals are going to break. All right, metal structures, they have a sea of electrons, okay, and they form mostly in a hexagonal layer or cubic centerment arrangement. So, but basically what causes the metallic structure to be a high melting point is the number of sea of electrons in their structure. So copper, aluminum, all metals, iron, they have a sea of electrons, particles that are present. There's positive ions and then the sea of electrons around. Delocalized electrons are what keep the forces together. They're solid at room temperature, high melting point, hard and malleable, so they don't break. They conduct electricity, is very good, and they're not soluble in water, so you can't dissolve metals in water. So you can see the destructive forces in metals are the high tensile strength or high hardness is because of the sea of electrons. And you can put stress on it, so you may bend them basically, is not breaking, but you're stressing them, pushing them to make them into a shape like a piece of plate or wire. So there's another image of the sea of electrons conductivity. So the reason why you can conduct electricity through wire is because of the electrons going through the sea of electrons. Alloys are a mixture of metals. So you have two or more metals that make up the alloy. So for example, copper and zinc are what makes up brass. And what the reason why you have alloys is make them stronger, make them more malleable, some make it cheaper. Okay, so you have different structure, different properties you want. You can do different alloys. Gold rings are an alloy. So a solid solution, B is an A. So there's two types of alloys. You have substitutional and institutional. Basically, it's just about the size of the atom. So why is brass stronger than copper? So when you put stress on an alloy, it doesn't, with a bigger atom, it's absorbing that energy, so you can't change it as much. You can't put a bent to it. So as you push it or try to make it more malleable, the bigger atoms kind of like take the force in and you can't break it or bend it. Where copper has all the single atoms, they're all the same shape, basically. It's easier to bend. All right, so aluminum is soft, it's lightweight, it conducts high electricity, but pure aluminum is very low strength because it's soft. So when you mix it with other alloys like copper, magnesium, silicon, you make it, whether it's resistant to corrosion or stronger or even lighter weight, especially with manganese and silicon, you have different properties. So it causes the density to be lower, has higher strength, and better resistance. Some examples are aircrafts, cinder blocks and engines, on bicycle frames. All those are good examples that make an alloy makes things better. All right, simple molecular structures. These are your gases basically, some solids, but they have a weak van der Waals forces, but they also form, some can form an crystal structure if they're solid. Okay, so this is between the molecules. You can see forming a crystal structure, but they do have weak van der Waals forces. That's why you can make them to gases very easily. Within the molecule, they have covalent bonding, which is a strong bond. So you're not breaking the molecule apart. You're just breaking the molecules apart. Molecules from molecules instead of breaking the atoms from the molecules. So strong covalent bonds are within the actual molecule, and then the VDW are between the molecules itself. So very little energy is required to overcome van der Waals forces, but you need a lot of energy to overcome the covalent bond. So simple molecular: iodine, bromine, carbon dioxide, a liquid, a solid, a gas. These are molecules, very weak intermolecular forces, but there's covalent bonds within the molecule. They're all three phases: low melting points and boiling points, very soft. They do not conduct electricity, and usually insoluble. There's some cases that are soluble in water, but most of them are insoluble. Okay, so you look at the properties between these different structures: aluminum, iron, copper, and sulfur. You can see sulfur breaks very easily. That's why it's a molecule, where these are metals. Density is relatively similar to aluminum, but you see iron and copper are very high dense. And you can see conductivity is very low for sulfur compared to the other metals. Giant molecular structures, these are big covalent compounds, graphite, diamond, silicon dioxide. The cool thing about this is that they have very strong covalent bonds, especially in carbon silicon structures. So you have diamond is a tetrahedral shape, graphite has sp2 hybridization, so they're called layers. And then silica or sand, silicon dioxide, also a tetrahedral shape like diamond. So elements such as carbon and compounds like silicon dioxide are giant molecular structures. Allotropes are the same element but different forms. So graphene, graphite, diamond, buckyballs, all those are common carbon structures. They all came from the same element. So graphite, very strong covalent compounds, but they're weak forces holding the layers together. That's why graphite is slippery and sometimes can be used as a lubricant. So if you're touch like mechanical pencil lead, graphite, you can feel it kind of slippery. And using it as chalk or like charcoal, it's also in your drawings. That's why it's slippery. The carbon atoms form layers, and the reason why graphite can conduct electricity because these bonds that are between the layers are delocalized electrons. So electrons can actually travel through, produce some electricity conductivity with graphite. These are hexagon layers, and again, high melting point, boiling points, and due to their strong covalent compounds, or strong covalent bonds. It's soft, and that's because it has layers, because there's only really 3 bonds between the carbons. The extra bond is the delocalized electrons between the layers. Good conductor due to delocalized electrons between the layers. Okay. That 4th electron that's where the bond is, and call 4 bonds around carbon. Diamond, on the hand, has 4 bonds strictly. It's a crystal structure, tetrahedral shape, very strong, high melting point. It's difficult to break. It's one of the hardest structures or elements out there, diamond structure. And that's because of the 3D covalent compound. So it's all covalent bonds. There's no delocalized electrons in diamond. So it doesn't conduct electricity because all the bonds, all the 4 bonds are involved between atoms. Silicon dioxide is very similar. This is sand. Sand is very high melting point. Graphite, silicon dioxide, diamond, silicon dioxide, they are made up of atoms. Very strong covalent bonds. It's a solid state. Very, very high melting points. Hardness is very hard. They do not conduct electricity except graphite, and they're not soluble in water. All right. Only homework question is to explain the properties of silicon dioxide, or SiO2, referring to its structure and bonding. So remember, structure is 3D tetrahedral shape, bonding is covalent. So why does it have a high melting point? Why does it not conduct electricity? Why is it crystalline solid? And why is it hard? So some of these could overlap. Pretty simple question, but basically just think about its structure, its bonding, and answer these 4 properties. All right, that's it. Less than 15 minutes. All right, any questions, let me know.